Today's video lecture we'll talk about section 6.1 that deals with solving initial value problems. So chapter 6 deals primarily with solving ordinary differential equations, or ODEs. If you took a Calculus 1 course here, you saw a bit of ordinary differential equations, and you may have taken the actual ODE class with Dr. Burney. So we'll look at a bit of review for solving ODEs and numerical methods associated with solving them numerically. So here we have a first order differential equation. First order because it deals with just the first derivative. And this derivative is given as some function of time, and the original function y. So here we see that the rate of change, that's our y prime, is dealing with the is defined in terms of the quantity y and at some present time t. Differential equations are used in modeling of various situations involving rates and how things change over time. So the solution to a differential equation is some function y of t, right? So when we solve a differential equation, we're looking for the function that is described by the rate, okay? So as an example, we want to show that the function y of t equals t sine t is a solution to this differential equation right here, okay? So let's look. So to show that this function y of t equals t sine t satisfies y plus t squared cos t equals ty prime. Okay. So to do that, all we need to do is to check to see if we were to plug in t sine t for our y's and the derivative of this guy for y prime, that we get an equality on both sides. Okay. So the first thing we should do is probably solve or find y prime. So y prime of t will be equal to, so note that we're taking the derivative with respect to time here, so we'll need to use the product rule. This product rule states we're going to do the derivative of the first one, which is 1 times the second, plus the derivative of the second function, which is cosine, times the first, or sine t plus t cos t. Now let's substitute in our values for y and y prime here into this differential equation. So y becomes t sine t plus t squared cos t equals t times our y prime, which is this guy here, sine t plus t cos t. You can see that when we distribute the t, we get exactly the left-hand side here. So we have equality. This implies y is a solution of the ODE. Okay. So, this is just one such solution. There may be other solutions that satisfy this differential equation, but we have found that this is one of those solutions. Okay. All right. So depending on some initial condition, we can get various solutions for a particular ODE. So together with an initial condition and the ODE on some interval a to b for time, we have what is called an initial value problem. So here you can see the setup for an initial value problem. We'll be given the rate, y prime, as some function of t and y. We'll be given some initial conditions, so we know one solution on the one value of the solution on our interval a to b. In fact, the initial condition will always be the first value of y for the first value of t. So to visualize some ODE, we make what is called a slope field, because there are, in cases, infinitely many solutions for an ordinary differential equation. So here we can see the slope field for a specific ODE. Right. So basically what a slope field is that we are using y prime to calculate the slope of some tangent line to the solution curve at various points in the ty plane. Okay, so you can see here, if we zoom in a little bit, so it looks like at here we're going from t is going from 0 to 2, and basically all of these little arrows are the slopes of the tangent line to the curve at various points within the ty plane. So you can see here the solution along when y is 1 for all t values along this interval. So if we have an initial condition where, let's say, y of 0 is 1, we will get this horizontal line as our solution. However, when t is, let's say, something smaller than 1, let's say 0.2 right here, the solution curve will follow these arrows, creating one such solution. So you can see for various different starting points, we'll get different solutions for our differential equation. So over here we can see a couple of the solution curves drawn on the slope field. So it looks like when the t is 0 and y is 0.2, we get this solution curve here. When t is 0 and y is known to be, let's say, 1.4, we get this solution curve here. Okay? So depending on that initial condition, it gives us a different solution for our initial value problem. Okay? So in fact, here we see that this is the solution to the initial value problem for this differential equation with various y naughts there. All right, so before we get into the numerical methods associated with differential equations, let's find out how to solve them analytically. So there are several methods. If you took the ODE course, you know about the ones that we're about to do, but there are several that help us to solve various types of ODEs. One such method is called separation of variables. Okay, so just as the name suggests, what we're going to do is separate the variables y and t to either side of the equation, and then we're going to integrate. So let's see how we do it for this example here. So we want to solve y prime equals 5ty with initial condition y0 equals 1. So effectively what we try to do is separate this, right? So since y prime can be denoted as dy dt, what we're going to try to do is try to separate the differentials and the terms involving t and y to either side of the equation here. So the first thing that we would want to do, we can, if you see here, we can multiply by dt on both sides of the equation. Produces dy equals 5t times y dt. Right? So if this y weren't here, we would be able to integrate this side. So let's move the y over by division. So we divide both sides by y, we get 1 over y dy equals 5t dt. So effectively what we've done is just separated the variables and differentials here. So now that we have an appropriate form for integration, because we have some function of y times the differential equal to some function of t times its differential. So here we're going to integrate both sides. And do the integration here. So the integral of 1 over y dy is the natural log of absolute y. That's equal to the antiderivative of 5t with respect to t is 5 halves t squared plus a constant. So here I didn't put the plus a constant on the sides because we can just absorb it into this one. So I just leave it to the right-hand side here, okay? So note that here, all of the solutions to this differential equation will have this kind of form to them. We can actually do one more thing if we exponentiate both sides. That is, exponentiate here, cancel our natural log, so we have absolute y is equal to e to the 5 halves t squared plus c. Now, using our initial condition, we can find the specific solution for this problem. We know that y of 0 is equal to 1. So that means y of 0 is equal to 1. So that means if we input 0 for t and 1 for y, we can solve for c. Okay? So here, using the initial condition, we get the absolute value of 1 is equal to e to the 5 halves times 0 squared plus c, which equals 1. This will be e to the c. And taking the natural log of both sides, gives us 0 here. The natural log of e to the c is equivalent to c times the natural log of e. And the natural log of e is 1, so c is 0. Therefore, our solution to this problem is absolute value y equals e to the 5 halves t squared. Now, in fact, because e to the 5 halves t squared only outputs positive values, then we can actually write the solution without the absolute value symbols, like this. Okay? So here is our solution. Now, as for problems that are not separable, because all ODEs are not separable. In fact, ODEs in the form y prime equals some function of t times y plus h of t, or a first order linear ODE. There is a separate method for solving the problem. As you can see with this particular example here, y prime equals ty plus t cubed. There would be no way to get the y term over to the left-hand side as a product with the differential dy. So we have to have a separate method in order to solve these types of problems, okay? So how do we do it? Well, we use a trick. In fact, we multiply by what is known as the integrating factor. The integrating factor is e to the power of negative integral of g of t dt. That g of t comes from this function here, okay? So if the integrating factor can be expressed simply, then we should have a shot at getting the analytic solution to our problem, okay? So let's look at why the integrating factor works. Why does the integrating factor work? Okay. So if we consider this function here, y prime equals g of t y plus h of t. Okay. So what we're going to do is multiply both sides of this equation by our integrating factor. Okay, so let's do that. So we'll multiply both sides by e to the negative integral of g of t dt times our y prime equals, we're going to multiply this side as well, so I'll just write it. Times y plus integrating factor times h of t. Okay. All right, so now what I can do, I can move this term, this entire term, to the left-hand side. So we'll get e to the negative integral g of t dt times y prime minus this whole term here, e to the negative integral of g of t dt g of t y equals h of t. Okay. Now, here's the trick. This is the reason why it works. So if you notice on this side, let's call this star. Okay. On the left-hand side of star here, we have a particular form. So notice that the derivative of, let's say, y times e to the negative integral g of t dt prime. What would the derivative of this function be? Y times our integrating factor. Well, we would have to use, this is the derivative with respect to t, we'd have to use the product rule along with a chain rule here, okay? So, the product rule says the derivative of the first times the second. So the derivative of y with respect to t is simply y prime times the second function, e to the negative integral of g of t dt, plus the derivative of this second function here. So what's the derivative of e to this power? Well, we know it's just going to be e to that power, but chain rule says we multiply by the derivative of that power. So what is the derivative of the negative integral of g of t dt? Well, the fundamental theorem says that the derivative of an integral is simply the integrand here. So the derivative of this is just negative g of t. Right? So it's the derivative of this first term times the second term, times y. If we kind of simplify this a little bit, we'll get e to the negative integral of g of t dt, y prime minus e to the negative integral g of t dt g of t y. Right? So notice that this is the right-hand side of our star here, right? So actually we can rewrite the left-hand side of star like this. So this implies that star is y times the integrating factor, the derivative is equal to up here we should have this term involved as well, e to the negative integral g of t dt. Or start from this term equals e to the negative integral g of t dt times h of t. Okay. So now we can integrate both sides again. So we're going to integrate this side with respect to t. And this side with respect to t. So a little bit more, we can get our analytic solution. So here we have the integral of some derivative with respect to t. So the fundamental theorem says we just get this guy here. So y times e to the negative integral of g of t dt equals this side. Finally, if we divide off this term, we get our solution, our y. So y is equal to, divide by e to the negative integral of gt is the same thing as e to the positive integral of g of t dt. Again, we would have 1 over this negative power. We can just write it as a positive power times this integral. Okay. So note that we have this right-hand side all in terms of t now. So as long as these integrals are relatively simple, we can find the solution for our differential equation. Okay. So let's try an example. So we want to solve the initial value problem. Y prime equals ty plus t cubed with y naught equal to 1. Okay. All right, so here we notice that this is a first order linear ODE, right? We have this addition of some other function, right? If we didn't have that, we could just use separation of variables to get the problem separated. But since we have this plus, that kind of gets in our way. So the thing that we want to do here is identify the integrating factor, multiply both sides by that, and then try and integrate it, right? So our integrating factor is e to the negative g of t. Well, g of t is that function that is on y here. So negative integral of t dt, which is e to the negative 1/2 t squared. And we'll omit the constant. Once we come toward, once we get to the end of the problem, we'll add that in for simplicity. Okay. So here is our integrating factor. We're going to multiply both sides of the equation by that. So we'll have e to the negative 1/2 t squared times y prime equals t e to the negative 1/2 t squared y plus t cubed e to the negative 1/2 t squared. Okay, so just multiplying all the terms by that integrating factor. Okay. Now, to use our trick, we need to move the term involving y to the left-hand side. So we'll get e to the negative 1/2 t squared y prime minus t e to the negative 1/2 t squared y equals t cubed e to the negative 1/2 t squared. Okay, recall that we can use our trick here. So this side can be represented as a derivative. It's a product rule type derivative. So this would be y times e to the negative 1/2 t squared prime. Okay. You can check to see that this derivative with respect to t yields this, equals our right-hand side. Now we integrate both sides, so the integral of this derivative is just what's inside here, equals the integral of this side. With respect to t. All right, now before we divide by this term here, let's go ahead and try to anti-differentiate this. So if you remember from your Calc 2 class, there are several methods to take care of this type of integral here. Now, it doesn't look like U substitution will work for us, but in fact, we can manipulate the U substitution in such a way that it will work. Okay, so we're going to let U, I'll let my U be equal to, let's make it equal to 1/2 t squared. Okay. So note that 2u is equal to t squared. Okay. And du will equal t dt. Okay. All right, so let's see what we have. So we have our left-hand side equals the integral. We can write this term pretty simply. That's just e to the negative u, right? That's e to the negative u. Now, what we need is a substitute for t cubed dt. T cubed dt can actually come from the product of these two sides here. So note that 2u du, 2u times du is equal to t squared times t dt. That's t cubed dt. Thus we can substitute t cubed dt for 2u du. Okay. So let's get the integral of 2u e to the negative u du. All right, so with that substitution, we have decluttered the integrand a bit. Now we need to think about how we take care of this antiderivative. This antiderivative can be attained by using integration by parts. So 2u is our u function, and e to the negative u du is our dv, right? So I'm going to state, so integration by parts. We use w equals 2u, and let's say dv is equal to e to the negative u. So dw is 2 du, and v is negative e to the negative u. Okay. So performing the integration by parts, we get y times e to the negative 1/2 t squared equals, so remember integration by parts, we'll have 2u times negative e to the negative u, so negative 2u e to the negative u, minus the integral of v dw in this case, so minus negative e to the negative u times 2 du. So that would be negative 2u, negative 2e to the negative u du. And this integral is doable here, right? So we get negative 2u e to the negative u minus this antiderivative, which would be 2e to the negative u plus c. Recall that we did a substitution on u, so let's plug back in what u is equal to. That's 1/2 t squared. So u times e to the negative 1/2 t squared equals negative 2 times 1/2 t squared e to the negative 1/2 t squared minus 2e to the negative 1/2 t squared plus c. All that's left to do is divide by our e to the negative 1/2 t squared. So y will equal, simplify here, so that's going to give us negative t squared. And we're dividing this entire term by e to the negative 1/2 t squared. So those guys are going to cancel. So just left with negative t squared there. Minus 2, these guys are going to cancel, plus c divided by e to the negative 1/2 t squared is the same as times e to the positive 1/2 t squared. Okay, so here is our general solution for the problem. We now need to apply the initial condition to solve for our particular solution. So using y0 equal to 1, we'll get 1 equals, we'll plug it in 0 for our t's, so that would be 0, minus 2, plus c, e to the 0 is 1. Okay? So adding 2 over, c is 3. Therefore our solution is y equals negative t squared minus 2 plus 3 e to the 1/2 t squared. So you can see here the integral was kind of complex. We had to do a u sub and an integration by parts. And that comes from the fact that we had that t cubed as h, right? So depending on the complexity of your g of t and your h of t, it can result in a rather hairy integral. But I believe the ones in homework are less complex than this. All right, so this is how we find solutions analytically. Of course, in this class, our aim is to figure out methods for solving by numerical methods, right? So we have a couple of different ways, separation of variables and this integrating factor to solve analytically. But of course, we're going to run into situations where the differential equation has no analytic solution, and we have to use approximating techniques. The most simple is called Euler's method. Okay. So again, many times it's impossible to solve an ODE analytically, so we need a numerical approximating tool to do so. Euler's method is an iterative method that uses the idea of local linearity or linear approximation to draw small tangent lines over a short distance to approximate the solution to an initial value problem. So Euler's method takes on our initial condition, why not, and then iterates to find the numerical approximations to the function values for our function y. So here you can see that the next approximation depends upon the previous approximation plus some h value times the derivative. Remember, f is the value of y prime at ti and wi. So again, each wi plus 1 approximates y of t plus 1. H is the distance between the t's, any two t's, successive t's that is. We call this the step size. And then the error associated with the approximation is the actual value yi minus wi. Okay? So let's look at a derivation of the method. Okay, so we have consider the initial value problem, where y prime is given as some function of t and y, and let's say y of a is y sub a, and t is in a to b. Okay. So let's take a look at a graph. So say we have this function here. This is our y of t. So here we have a t-axis and a y-axis. Okay. And let's say here we have A, here we have B. So what Euler's method does is it uses the slope of tangent lines to the function to approximate the next solution value, right? So let's say we have t0, A is t0, and then we have this t1 here, okay? So that means that we have a function value which is known, right? Because we know the first value of the function, the initial condition, is this guy here, which is, let's say, y sub 0, right? Or we can define this as w0. So the approximation and the solution value are the same. We know the first value, first point on this function. So what Euler's method does is it uses a tangent line at this point to approximate the function value here. So if we kind of draw a tangent line to the function, here's our tangent line. So the actual function value here, this would be y1. Right? Euler's method approximates this point on the function to be this point right here. Okay? So that would be maybe right about there. We'll call that W1. Okay. Then what happens is that once we know W1, we use another tangent line to approximate the solution at, let's say, some T2 value. So T2 is there. We use another tangent line using the slope from the function itself. So the slope is here, something like that, to approximate the solution at T2. Right, so the difference here is our Y2, here's our W2. Right. So you can see that there's a bit of error involved. So the error is just that distance. That's our error. Okay, at each step. So how do we figure that out? So again, here's our Y1, here's our W1. Again, the error associated there would be that difference in the two values. So how do we find this guy here? Well, of course, we would continue that if we did it in 3 time steps. Let's say that's T3. We would do it one more time to get the approximation at the last value. Here, here, that would be Y3 is approximated by W3. Okay. And again, the difference in the t's is h. So this distance here is h. This distance here is h. This distance here would be h. Okay? So again, let's see how we get the approximation for W1. Well, we use this line. So what is the equation of this first tangent line? It's the equation of the first tangent line. Well, let's see. In order to find the equation of this line, we need a point on the line, which we have initially. We have this point. And we need the slope of this line. Well, the slope of this line comes from the first derivative, which is known from the initial value problem, right? Y prime at ft naught y naught is known. So y prime at t naught y naught, or y prime at t naught w naught, right? We've defined y naught to be w naught, is known. This is the slope of the tangent line. We can call this f of t naught w naught. That's our slope. We know the point on the line is t naught w naught. Okay. So the equation of this line would be y minus w naught equals our slope times t minus t value here, t naught. Right? I'm just using the y minus y1 equals m times x minus x1. Okay? So we know that this is going to approximate another point on the line. Well, what's this point? This point is T1, comma, W1. So because T1, W1 is on this line, then, well, our y value would become W1 minus W0 equals F T0 W0 times T1 minus T0. So the value of W1 is equal to, if we just add this W0 over to the right-hand side. So W1 will equal, we're adding W0, so let's say W0 plus this product, right? W0 plus this product. Well, what's T1 minus T0? Well, that's just the distance between T1 and T0. That's H. So here we have H times F of T0. We can do the same analysis now that W1 is known. We can produce the tangent line there, and we would find that W2 would equal W1 plus H times F of T1 W1. And W3 would be W2 plus H times F of T2 W2. Now that W2 would be known, and T2, of course, is already known. So continuing that iteratively, we can do that up until the very last value here. So here, Wi plus H. Of course, we can do that iteratively, so the next approximation is the previous approximation plus H times the slope at the previous approximation, Ti, Wi. Okay? And of course, the error is just the difference. If the solution is known, the difference between the solution and the approximation would be our error. Okay? All right, so let's try an example. So we're going to apply Euler's method to the initial value problem from the previous example. So that was by Euler's method with H equal to 0.1 and H equals 0.2. We'll do 0.2 first. So let's say 0.2 and 0.1. And then we want to investigate the errors there. So our initial value problem was y prime equals t y plus t cubed. Okay. The initial condition was y of 0 equals 1. And we're on the interval 0 to 1. Okay. So if H is 0.2, then we need to partition our axis, t-axis, to find the specific t values we want to evaluate at. So it would be 0.2, 0.4, 0.6, 0.8. Okay. So the only value that we know so far is the y-coordinate for when t is 0, and that would be equal to 1. Right? We're going to use Euler's method to approximate the y value at t equals -2, and then iteratively until we get the solution at t equals 1. Okay? So let's do our, so what do we know? We know that W naught equals Y naught, which is 1. Okay? So the formula for Euler's method in this problem would be yi plus 1 equals, wi plus 1 equals wi plus h times f of ti wi. So here's our f function, right? This is our f of ty function. So that would be ti times wi plus ti cubed. So all we need to do is just plug in and then use our next approximation. So let's look at W1 would be W0 plus H times T0 times W0 plus T0 cubed. So what is that? Well, what's W0? That's 1. Plus, what's H? 0.2. Times, what is T0? That's 0. Times W0, which is 1. Plus T0 cubed, that's 0 cubed. So that is also 1. Okay. W2 would be W1 plus H times T1 W1 plus T1 cubed. Okay. So again, here's our T0, here's our T1. So now we're changing it to 0.2. So let's see what we get. What's W1? Well, that came from the last iteration. 1 plus, our H is 0.2 first, times T1 is 0.2, times W1, which is 1, plus 0.2 cubed. Let's see what that gives us. So I'm getting 1.0416. Okay. Let's do it again. W3 would be the previous approximation, 1.0416 plus H is 0.2. Now we're at T2. T2 is 0.4. So 0.4 times previous approximation plus 0.4 to the third. Let's see what that gives us. Getting 1.137728. Continuing on, W4 would equal the previous value, 0.2 times. Now our next T is 0.6. See what that gives us. 1.287055536. All right, now we're at our, this is our last approximation, right? If you notice, we're getting an approximation, so we knew W0. We got an approximation for W1, W2, W3, and W4. And W4 is used for the very last value here. So one more iteration is needed. So that would be previous approximation times nu t is 0.8 plus 0.8 cubed. Getting 1.595384218. Okay. So our approximate solution when t is 1 is this value right here. Okay. Now we can investigate the error by knowing the exact values. So we have the solution from the previous example, right? So let's make a little table. So here when t, let's do t, let's do our approximation. WI, so this is TI. Our approximation, our exact value, and then our error. Alright, so our t's were 0.2.468. Okay. So at 0, it is known that these two values are the same, right? So that would be 1 and 1. So the error is 0, of course, it's known. Now at 0.2, our approximated value was 1. Now let's look for the exact solution. So recall that our exact solution for this problem was this right here, right? So let's plug in our t value and see what we get. So negative 0.2 squared minus 2 plus 3e to the 1/2 times 0.2 squared. So the exact value to 60402. So our error is 0.02061402. Okay. At 0.4, our approximation was, so this is W, so let's say I. 0, 1, 2, 3, 4, 5. So we're looking at W2 approximation. That was 1.0416. And let's calculate this guy here. So we'll just go back, change all those 0.2s to 0.4s. So it looks like 1.08986123. Subtracting for our error gives 0.04826. 1203. At W3, our approximation was this, and our exact solution, just go back and change 0.4s to 0.6s. That's 1.231652089. Getting 0.093924 about. For when t is 0.8. Gives us 1.4913833293. Subtracting our approximation. Is 0.204327, let's say 2a. So you can see our error is increasing. And then finally, $1.946163812. Gives us 0.35078 approximately. Okay. So we can see here that the error is increasing as we go. Of course, the error is compounded because we're using approximations to generate these values. Okay. We can actually control this a little bit, as if we only limit ourselves to approximations on short spans of t and with small values of h. Okay? So if we do the same thing for 0.1, let's see what happens to our error. All right, so we won't go through and do it for 0.1. We would have to do 10 iterations of that. So you can see how to do that. You can check to see that this table is going to be correct. But if you look here in your book at this table here are the iterations associated with h being 0.1. So notice we would partition by 0.1s on our t-axis, 0, 0.1, 0.2, 0.3, all the way to 1. So we'd have double the number of intervals here. Here are our approximations. Here are our exact solutions. And here are the errors. Okay. So if you notice, on the first iteration, we get 0 error. On the second first iteration after the initial one, 0.005. And that's when at 0.1. Now if we look at 0.2, that was our first iteration here, right? Let's notice what's happening to the error. So here the error is 0.01 approximately. Our error was 0.02. So you can see it's about half of that. Here if we go to the next iteration, for 0.4, we have 0.025 as our error. Here we have about 0.05. It's also half, right? And continuing that on at 0.6, if you notice, 0.04 is 0.0497 is about half of 0.09, and so on and so forth. So when we half the step size, we half the error at each of the approximations. So with h small, we have a better approximation. But it requires, of course, more computation, so there's no free lunch here with Euler's method. All right? So you should be able, I have some pseudocode for you for your computer problem. So for your pseudocode, you're going to make a function file, maybe call it Euler, and you want to pass it some value, some variables here. So you want to pass it the y prime equation. You know how to make, to define a function in MATLAB. You want to pass it the t interval, the time step h, and the initial condition, why not? Then partition the t interval into the appropriate subintervals using h, you save that as a vector, and then apply Euler's method using a for loop. Okay? So you should be able to do the homework problems now. Exercise 1 deals with example 1 that we did in the notes. 3 and 4 deal with solving analytically, and 5 deals with applying Euler's method. Computer problem 1, of course, you'll implement Euler's method using MATLAB for the previous problems. Okay, so notice that part 3, exercise 3, exercise 5, and the computer problem all deal with the same example or exercise, and you'll be doing just parts A, B, and F for those 3 there. If you have any questions, feel free to email them to me or set up a Google Meet session with me.